the thing I'm going to present today is actually quite straightforward. However, I will have to do some introductions to make sure you know what's going on. So to everyone who has already seen part of the content, especially my seminar in March, I'm truly sorry, but I have to go through that because otherwise it wouldn't be understandable. Okay, so the first introduction I need to make is about the adversarial examples in the misinformation space. So we know what misinformation is, right? So not everything you see on the internet is true. This is a nice example, quite a new one. So probably I don't have to tell you this is not a real picture, and this event actually didn't happen. However, you can see tweets like that share information that is quite obviously untrue. So the motivation is, the overall motivation is to find information like that and tackle it properly. And this is not only a social problem, but it's also a computational problem. So you can very easily see it as a binary classification problem, right? So you can build a classifier essentially that classifies credibility of content with very, very simple steps. So first of all, well, this is not very well seen, but you have to gather examples of both credible content and non-credible content, which is plenty on the internet. You hire some expert that can provide you with credibility labels that say whether this content is acceptable or not. And then you use binary classification, which is probably the best known task in all of machine learning. So it's very well known. And then you deploy it. So super easy. And also you can apply it to not only to credibility, but you can also detect content that is inflammatory, violent, or simply put, illegal, right? And there's a lot of literature in natural language processing for different types of undesirable content like that. So fake news is a famous example. This is where it all started. But we also have hoaxes, bot-generated content, rumors, false claims, hyper-partisan reporting, and also propaganda techniques. For each of those, there are data sets where people have gathered content, and they ask experts, usually journalists, researchers, that annotated them with respect to certain categories. And then you can just build the classifier. And yeah, and it's used very widely. Unfortunately, big platforms that host user-generated content don't normally share information about what kind of technology they use. But when something goes wrong, we can often see that. So the last case when something gone wrong was when Elon Musk fired majority of people in Twitter. And you can immediately see that the type of misinformation that was showing up, the type of inflammatory content was consistent with the usage of simple machine learning classifier. So ideally, you would want a classifier to work like that it's used just to prioritize content, and then a person makes the final decision whether certain information is acceptable or not. But often it doesn't work that way, and then you have only a machine essentially deciding what is being published and what isn't. Which brings the question, is it really acceptable for an algorithm to decide what kind of content is published in media that are the majority source for news and other information for many people, right? So this brings like a very big social role for these algorithms, and the research I'm going to be presenting is looking into whether these algorithms are up to the job, right? So the problem is that this situation is adversarial. So what it means is if you have a certain social network that's using this type of content filtering, and then you have an example information that is being propagated, this is actually true. I mean, it's fake, but it's actually true information that was shared in 2020 by unknown actors in Polish internet. And then message can get recognized as misleading, and then it can be blocked. This often happens in a way that the first message is noticed by someone, and then everything that is similar to this message is blocked as well, right? So what will the person that is disseminating this message going to do? They're probably not going to just give up, right? So what they're going to try to do is use different rephrasings and then find a variant that gets through, right? So for example, let's imagine that instead of approaching, we change it to coming, and this sentence is not recognized as being the same, and then it gets true, right? So this type of example we call adversarial example, right? Okay, this is clear. You remember from the last time? Okay.
So it's just a clarification question because I don't know how classifiers work. Are they so literal that just by changing word?
Not all of them, not equally, but many, yes.
Okay.
So especially neural networks are famous for that.
Okay.
Okay, so this is an example from not from misinformation, but this is from spam filter. So if you look into your spam folder on Gmail especially, you can see that there's many emails that try to send academic spam, and then they try to get through the filters, but by using non-standard letters, right? So, for example, unsubscribe, and instead of U, I don't know what this character is, but it looks like a U. This is a Greek kappa, and this is the Russian character, which I don't know how it's called. And in English, I don't know how it's called. Okay, so this already happens, right? This already happens. So to be a bit more formal about that, so we have a classification task. A classification task is defined by a training set and an attack set, and each of those has a feature, it consists of examples, and then each example is described by some features and then some label, right? And what the model does, the model we will be attacking, we call it victim model. It's just predicting the label based on the example, right? So it's just, you can see it as a function. And what we are seeking when we are looking for adversarial examples is we are looking for a modification function M that satisfies two criteria that are equally valid. So the first one is the victim changes its decision. So this function, the prediction based on the modified example is different from the prediction on the original example. And then it preserves similarity. So we want the modified example to be still roughly similar to the original. Because if you change it so much that it's not similar at all, then it's useless. Okay. So why do we do that at all, right? Because I don't plan to attack Twitter with fake information, but it's also important to do that in a research setting. So the first thing we do is we can assess the robustness of classifiers. So by robustness, I mean the ability to deliver the correct results, even if the producer of the content is trying actively to deceive the classifier, right? And this can be computed, this can be measured, and then you can, when the time comes to deploy a classifier in an adversarial scenario, you can choose architecture that is more adversarial. Right? Second thing you can do is that you can train more robust classifiers. So this is called adversarial training, and here you use the examples that you generate to improve the robustness of the classifier. The most trivial way to do it is you take adversarial examples and you add them to the training data, right? So you would expect that the classifier will know that, I don't know, changing B into Miatki-Znak doesn't change the meaning. But there are more elaborate ways to do that. And then finally, for better understanding of how the models work. So this is Diego's question. So this whole field emerged when people noticed that neural networks are extremely vulnerable to these operations, right? That's because of the nature of the decision boundary, which is not a line, right? It's not a linear classifier, but it's extremely wavy. So sometimes you can make a very small change to change the decision. So by researching adversarial examples, we're also learning something about how the networks work, or any classifier for that matter. And then obviously, these vulnerabilities, they exist, whether we like it or not. So I think it's better that we discover them here as part of the research, rather than if they would be discovered by someone hidden in their server trying to attack it, right? And just like with any vulnerabilities, they should be publicized rather than hidden. Okay, is that roughly clear? Okay, so now I'm going to move on to the motivation of this contribution. So what I'm going to add to the common framework is add some adaptation. And what does it mean to adapt and how we do it? So how these attackers work is actually quite similar one to another. So I'm using the example of BERT attack, but actually they all work in a fairly similar way. So they observe the input text, and then the classifier response. Let's say it's correctly detected as misinformation. And then you heuristically choose one of the tokens that you're going to be modifying. So let's say it's causes, because causality is quite often an important aspect of this. And then you just make some modifications, right? So you can replace the word that you are targeting with a synonym, like one of these. You can attack a single character and add the Greek letter. You can change a grammatical form. The sentence doesn't make sense anymore, but it's all right, because when you're reading, you don't, spell check everything. So various types of modifications, but they have the thing they have in common is they preserve the overall meaning, but change the representation of the text for the victim. And then you check whether the decision of the classifier is changed, right? So you just send the new text to the victim classifier. You ask it for its decision. If the decision is changed, bingo, you've got the adversarial example. However, typically you wouldn't find it by just making one change, right? So when you don't find one, you go back to step 2 and you choose another token, and you keep on modifying until you get an adversarial example, or until the text becomes so different from the original that it's pointless to continue. Right? So this is the overall schema, and once you do that, you get the next example, right? So we would like to add some adaptation. Anyone sees where's the weakness here? So the weakness is that when you do that, there is no point where we are actually remembering what kind of modifications work and what doesn't, right? Because let's say we're trying to come up with modifications for a campaign, a misinformation campaign that has 400 tweets, right? And if changing causes into provokes makes it work, you would probably want to remember this information when you are attacking the next text and the next one and the next one, right? Instead, here we just.
But we don't really know whether this change will work for a different sentence.
Very good point. Sometimes it will, sometimes it won't. But the victim classifier is the same. So the hypothesis is there are some inherent vulnerabilities of the model that do not depend on the sentence, which we'll see whether it's really that. Okay. Just some example when actually the traditional workflow works, right? So this is a sentence that we change from homes to houses, right? And the decision of the classifier, originally it was that this is reliable information, and now it says this is using propaganda techniques for some reason, right? Here we change the comma to a question mark, and then again, this inference was true. I think, yeah, this inference was true, but now the classifier says this inference is false. And this one is, again, propaganda. We change explain to explained. The sentence is not grammatical anymore, but again, doesn't matter if you're reading fast, and the decision of the classifier is different. So why we want to do these attacks? So first of all, we are gathering a lot of information in this process, and then we're just throwing it away, right? We're throwing away the information, what worked and what didn't work. So the idea is to learn from these successes and failures. First thing that it will allow us is just find better adversarial examples when we've had more information about the attacked classifier. But the second thing is we're doing all that to simulate real world attacks, right? So we want to be a bit like real world attackers. And real world attackers are not individuals, but they are quite typically institutions, right? So this is the famous Russian Internet Research Agency. It's an institution with a budget with many years of experience. So you can imagine that they will be doing the same thing. They will be gathering information about how the classifiers used for content filtering work in big media, Twitter, Facebook, whatever, and they will be using this information. So if we want to prevent such attacks, we want to be able to also build adaptive attacks. The thing. Okay. So this is the second point when I'm saying I'm sorry, because I need to do some explanation to reinforcement learning. So sorry to those who had a decent machine learning course and know all about it. Everyone else maybe will learn something. So we are going to build a model that is not a classifier anymore, but it's an agent, right? So it's an agent that makes certain actions in the environment, observes what works and what doesn't work, and then gets rewards that represent the quality of the action, and uses this information to improve its behavior step by step, right? So the way to do it is reinforcement learning. This is the framework designed traditionally. What we want to achieve in the end is to come up with a strategy for choosing actions that will maximize the received benefits. Okay, so this is the reinforcement learning procedure. We have our agent, and we have the environment, and it's just happening in discrete time steps. In every time step, you observe the current state. What's the situation currently? You choose an action according to some policy. You perform that action, and in response to this action from a discrete set, you observe a certain reward. So the environment is telling the agent how good was this action, and then it's telling it the next step, right? And what you get is what we call an experience. So these 4 quantities get stored, and you can use them to learn. Now, the important aspect is this is not a classification or a regression task just for maximizing this R. Can you see why? Because what will happen is sometimes it may be good to choose an action that leads to small reward, but it brings you to a state that is way better, right? So not the greedy strategy is not always the best, right? Sometimes you have to study whole night to pass an exam the next day, right? The same here. Sometimes it's good to have small rewards now if you know that it's going to bring you into a state that will give you larger rewards later. Okay. So how to do that is going to get a bit mathy. So one of the established ways to approach this problem is called Q-learning. And Q-learning is built around the function Q. And the function Q represents a very simple thing. How many rewards we accept to get if, while being in state X, we perform action A, right? So this is a random because we don't know what the environment will do. The environment is not defined, but it can be expressed as an expectation of this is the reward function distribution. So the reward that we expect from this behavior is the reward that we get in this step, plus the sum of all the rewards in the future if we follow certain behavior, right? And the important thing we do is we discount these. The discounting factor, this is the number between 0 and 1, and it tells you how much less faith you have in what happens in the future, right? So the current reward is counted as it is. The reward you expect from the next step is only counted as half, let's say, if the rewarding coefficient is half. The next one, 1/4, 1/8, and so on and so forth. Because you don't know, you're still learning, so you don't have certainty over whether the rewards you expect are really sure, right? So this is the way of expressing the low certainty on what will happen in the future. And yeah, so we will be trying to estimate this function because if we have this function, it's quite simple to find the best action, right? Because you can just choose the action that maximizes this value, right? So a strategy that is greedy with respect to Q function is actually optimal. Why? Because you not only take into account the reward, but you also take into account the rewards from the next steps, right? So it goes over this problem of greedy exploration. yeah, so how do we know this function? So it used to be done differently, but in 2024, we approximated with a neural network, right? So you have your neural network, which has certain parameters. You input the current state, and then the network outputs their expected rewards for every possible action. So if you are following the greedy strategy, you can just input your state, and then you can just observe which number is highest. So let's say this number is the highest, so you just choose action A2. But obviously you have to create this network, right? So we create this network by using the following update rule. So we're going to be observing some part of this Q function. So let's say you are in state X, you perform action A, and then you get certain reward. So this is part of your observation. And regarding the future, you add the discounting coefficient and you multiply it by the maximum of the next possible action, right? So this is your observed Q function. I mean, it's partially observed because it's observed with respect to reality and it's still expected with respect to the next step. And you compare this value with what neural networks as it was is telling you, and this difference is your loss function. And you just plug in the loss function into whatever algorithm you're using to train a neural network, and you move on, right? Okay, what do you think? Is that understandable or? So I've described these two elements, right? The search for adversarial example as a task and the reinforcement learning. And now it's time to marry these two. So how can we marry them? So this is our solution, which is known as which we call XARELLO. It's actually exploring adversarial examples using reinforcement learning optimization. And it has three elements. So the first element is an environment. The environment is a mapping between the adversarial example task and the reinforcement learning scheme, right? Because we have our task and we have to represent it in terms of states, rewards, actions, and so on to be able to apply the framework of reinforcement learning. So this is what we call an environment. The second thing is an optimizer. So this Q function has to be somehow designed, taking into account the textual nature of the problem. And then the attacker. And then the attacker is actual, how are we going to use the Q function to attack the victim. Okay, so let's go with the environment. So the environment has two elements. So the first element is the current form of text in current step. And then another thing the environment includes is also what was the victim's decision for the original text. Right? So we will be going step by step modifying the text. So it's quite obvious why the current text is necessary in the environment. But this second thing is maybe less obvious. This is because the attacker needs to know whether we are changing the decision from misinformation to not misinformation or the other way around, because different modifications will be useful for both ways. And actually attacks both ways are useful. We not only want to take misinformation and be treated as real text, but also the other way around. If you look at the reporting, for example, for the Russian bots contribution into vaccine debate, it's often both ways, because even if you want to solve distrust, you want to actually change the labels both ways. That's why we need to know which way are we going to be changing the labels. And then what's the action? So the action is just the position of the token it will be taking, and then which replacement candidate we are going to be replacing it with. So we have some pre-computed list of candidates for every word in a sentence, and then just these two numbers tell us what is the action. Okay, and the reward is the following. So if the victim changes decision, boom, we win, right? We win, so the reward is positive is 1. It can be a case that there is an illegal move. So sometimes there are changes that you can make. For example, you change a padding token in the input, right? So this is not allowed. You get -1 for that. But except for these two special cases, we are just looking at the difference between the probabilities of the target class of the victim classifier. This is just computationally complicated, but on the example, it will be very easy. So let's go step by step. So we have the following sentence: drinking orange juice causes death. This is not true, actually, if you're wondering. So the misinformation label is 1. And then you perform an action that changes the word causes to a word provokes, right? It's a reasonable change. And you get the new sentence. And let's say the probability of misinformation, according to the victim classifier, has fallen from 75% to 60%. So we have gained this 15%. So this 15% is our reward. This was a good change, right? In the next step, let's say we are changing drinking into consuming, right? And actually, this was not a good change, right? Because the classifier was at 60%, but now it's back to 68%. Now it's more certain that this is misinformation. So it was a bad change. So the reward for making this replacement is 8%, -8%, right? It's a penalty, essentially, not a reward. But let's say we have more luck later. So we change provokes into brings, right? And then the new sentence, consuming orange juice brings death, is actually not considered misinformation. We dropped from 68% to 47%. On the other side of the 50% borderline, classifier says this is actually a very true claim, right? So the reward is 1, and we win, right? This is what we call an episode. We will be doing many of these episodes. This is very important that we understand that. Is that clear? Sure?
So the percentage is, because the classifier is binary, right? But then you have these gradients.
Yeah. So the classifier is binary, but we assume that we have also information about this percentage, right? So
that comes from?
Well, every classifier used currently produces that. The only question is whether this information will be exposed to the user, right? So there are different attack models that assume different level of access, but every modern predictor produces these percentages. Okay, so we have to build an optimizer as well, right? Because we already know how we're going about it, but we need to estimate the Q function. So the Q function takes into account as I was saying, takes into account the state, which is the current value of the text, takes into account the position that we will be changing. So this is just the position of this text in the transformer tokenized text. And then we have certain candidates. So we choose one of these candidates. So the position is just represented through a transformer, some embedding, and then the candidate is using a static embedding. And then you have these two embeddings. These represent the action. We just use a linear layer to reduce the dimensionality. And then further step, produce 2 values, right? Can you see already why I need 2 values? Well, because I said that the value of the Q function will be different depending on whether you are in a state which indicates changing from misinformation to credible information or the other way around. So the value of endorses changing to promotes will be different if you are looking to make text may look more like misinformation or less like misinformation. Maybe not here, but for example, for Trump, the word Trump is super strong indicator of misinformation because like the current political issues are a very good topic for misinformation. So if you replace Trump by something else, this will probably have very different values in these 2 outputs. Okay, this sometimes happens. I don't know why. Let's see if I can click here. No, I'm sorry. This will have to be like that. Okay. That obviously clear or not quite clear or
The two values, can you repeat again? So one is going from misinformation to information, then while the other one is the other way.
yes,
Right.
they express the value of making this change in these two scenarios.
But why do you need two values? Suppose say a positive value and a negative. Why do you need to do?
Because it can be that making a certain change is good for both scenarios. It can be that it's good for one, but for another. It's not always like that, but the one will be the opposite of the other. I mean, in trivial cases, but not always. Okay, so how do we attack? So we have two phases. So unfortunately, this requires some training, right? These vulnerabilities are quite subtle, so we will need a certain amount of training. So to do that, we split the attack into two phases: the adaptation phase, in which we will be learning the properties of the victim, which we will be training our Q function, and then attack phase when we actually perform the attack. So in adaptation, we have an episode. So what I've shown you before, that was an episode. In episode, the attacker can make up to 5 steps, up to 5 changes. If it doesn't find an adversarial example in 5 changes, we just move on, right? And each text example, so each text is repeated for 5 episodes, right? So it gets 5 times trying to change the text in up to 5 changes. And then all of the text examples are processed for 20 epochs. So we go through examples like that. 20 epochs in each epoch, whatever, 400 texts, each text changed 5 times, up to 5 changes. So quite many steps. And we want to encourage exploration in this first phase. So we use what's called an epsilon exploration. So with some certain probability epsilon, totally random action is chosen. And then with probability 1 minus epsilon, we choose a greedy action. We choose an action that seems to maximize the Q function. And then the epsilon falls from 100 to 10%. So in the beginning, you choose totally randomly. Once you start understanding more, you choose the actions that are actually good. And this is only happening to 30% of epochs. Later on, we just only keep 10% of random steps. And then in the attack phase, you always choose the greedy action because we are only attacking. We will be evaluated based on this output. The optimizer is frozen. You're not learning anything anymore. And then there's quite a complicated, instead of having 5 episodes of 5 steps, you have a more elaborate scenario. We do 10 episodes of 5 steps, 5 episodes of 10 steps, and then less episodes, but longer, right? Because you want to try many times to make little change before you move to making more changes and more changes and more changes. Because you really want to find an adversarial example in very few changes, right? So it's worth trying many times before you move on. And also we use memory of previous experiences, but this is a reinforcement learning technique, but maybe I'll explain it if someone asks. It's interesting, but not crucial. Okay. Is that clear how we do it? Roughly. Ella is not so certain.
Well, I don't see all the stuff, so only by listening to you, it is not enough to understand every point.
Okay, there's a paper, so if you want to replicate it, the paper is available. And code as well. Okay, so let's just check if it works. So we'll be using another reminder. So we'll be using Bodega framework, which is a framework for evaluating the adversarial examples in misinformation domain. It has 4 tasks: news bias assessment, propaganda detection, fact checking, and rumor detection. 3 types of victim classifiers. 3 architectures, but each of these 3 architectures is trained for these 4 tasks. So we have 12 models in total. And then our measures of success is whether the classifier changed the decision, which is the most important thing, but it's not the only important thing because we want to keep the similarity. So the second thing is semantic similarity between the text, the adversarial example, original example, and then the character similarity score using edit distance. And then the Bodega score is the product of the above. So if you don't change the decision of the classifier, you get 0 points. However, if you change the decision of the classifier, but the similarity is none, then you get 0 points as well. You want to do both things. That's why it's a product. And we have some baseline from the literature, but also we have XARELLO raw. So what it does, it's a modification of this in a way that we don't do any adaptation. And we want to do it because we want to make sure that the gains we are observing are from adaptation, not from using a different attack procedure, right? Because we have this elaborate attack procedure. And for example, BERT attack is similar, but it's not exactly the same. So you want to isolate the influence of a different attack procedure from the influence of adaptation. The framework is available if you want to give it a try. There was a shared task, a ton of things in the project done. Okay, so the adaptation process. So these plots are for different victims and different tasks. So for example, this is BLSTM and propaganda recognition. Here we have on the x-axis, we have epochs. And here you have how many steps on average for each text you needed to achieve success. And this number goes between 5 and 25. Probably not obvious why. So you are doing 5 attempts to attack. In each of them, you're making up to 5 steps. So if you are the best algorithm in the world, you will find an adversarial example in the first try in each of these 5 steps. So the minimum number of steps you have to do for a given text is 5. However, if you do everything randomly, you will just run out of these tries. So you try 5 times, you do 5 steps each, and you never achieve success. So this number is between 5 and 25, and we want it to be as low as possible. Right? And you can indeed see that it goes down, right? Especially on training, right? It goes differently for different parts, but goes down, right? From 22 to whatever 12, right? So we were roughly half it. Now, it's very important to take into account these two lines, right? This is on training, and this is a separate evaluation set, right? Because we don't want a model that just memorizes what works for a certain sentence, right? Because that would be quite easy. You want a model that observes some general weaknesses, right? So this is about the question, right? That was asked earlier. It seems that apart from like memorizing what worked, there are some weaknesses of the victim model that could be transferred from the trained data to the evaluation data. Not one-on-one, so it's not the same line, but there is some gain as well. It's very, very big on fact checking because this is essentially natural language inference task, so it's quite easy to break it. It's very small gains on these two. So these are news bias assessment, and this is like a whole article. So what happens is it's quite rare that we manage to find adversarial example in these 5 steps, right? Because if the article has, I don't know, 200 words or 1,000 words, you will need to change more than 5 of these to achieve an adversarial example. So that's why the gains are small, but I can promise you, if you zoom in, you will see that there are some gains. So adaptation works. So how does it work in practice? So there will be many numbers, but in each slide, I want to just draw your attention to one thing. So what do these numbers mean? We have 3 victims. The task is propaganda, and we are measuring the bodega score. So the first line is the most important, and these constituent scores. Also, number of queries is important. How many queries you had to ask to find these adversarial examples. These are our 2 baselines, and this is XARELLO in the variant raw and in the variant full. So the way I described. So the first, you can see that indeed it works, at least on these, right? So when you had the BERT attack, which is a strong baseline, 52% of the score, the raw version is actually lower. So our attack procedure is a bit weaker. But if you add adaptation, you jump quite considerably to 60, right? And then between, it's quite consistent between victims, so it doesn't seem to depend on the victim. So you get a gain here, you get a gain here, and you get a gain here as well. Now, on fact checking, I want to show you another thing. So here what's very interesting is not only we get a better quality of the adversarial examples, but we also get them faster. So for example, if we're attacking BLSTM for fact checking task, you have 132 queries. So what it depends in real life, you type in something into Facebook interface, and Facebook tells you, I'm sorry, this text is inflammatory or whatever, rejects it. So you try again, and try sending 132 posts to Facebook, and you'll see how fast you're going to get banned, right? So these very high number of queries are just not realistic in real life, and we want to be realistic. And what this adaptation achieves, it allows you to find an adversarial example not in 130, but only in 5 queries, right? Which is totally understandable. It's because you have this knowledge accumulated from the past. Yes, in terms of rumor detection, that's here I want to emphasize the difference between victims. So the Bodega score for attacking LSTM, which is a very similar and old type of model, is 65%. If you go to BERT, which is generally a better classifier, the score goes down, which you would expect. It's harder to attack a better classifier because it understands paraphrasing better, for example. Right? However, if you go from like transformer model to super modern and large model from this year, well, this year, I think, from March, you actually go up, right? So what is happening here, and it's not only on our method, it's not the property of our method, on BERT attack as well. Look, you had Bodega score 292, 1.81, and suddenly you jump even above the LSTM. So what it means that these very large, very new models are actually quite vulnerable to attacks, right? Which is surprising. I'm not entirely sure why is that, because they generally understand the language better. So you would expect it's harder to fool them, but it's not. It's actually easier. Which is I think what's happening here. I think it has something to do not with the model itself, but the fact that you are fine-tuning the model on a relatively small data set. I think they are optimized towards prompting, but when you are fine-tuning, because we are fine-tuning a gemma here, it doesn't work as well. I mean, it works well for accuracy, but it's just very vulnerable to attacks. Okay, and this is for a change something that doesn't quite work. I mean, it kind of works, right? So BERT attack has 63, XARELLO roar has 49, and we go up to 61, but we don't beat the baseline. And this is because this is the hyper-partisan news, right? This is the data set when you have long news articles, and it's just not possible. I mean, it's possible, but it's very hard to explore the space, right? So the important aspect of any reinforcement learning algorithm is the size of the search space, how many possible actions we have, and how many changes we can make. So if we have 1,000 words, and then each of these words can be changing 10 times, and then you can have a sequence of words, then the search space is huge, right? And it doesn't quite, I mean, it does learn, right? Because we go from 50 to 60, it definitely learns, but it doesn't learn as well as for the other. But when it does find it, it finds it in left queries, right? So this is still calls, but the overall score is slightly lower. So it's slightly harder to attack this data set. Also because it doesn't quite understand all the weaknesses. So there are some, many of these models are very weak in terms of the ending of the text, right? So you can make very small changes in the last sentence and actually changes the whole setup. And it's hard to express this weakness in the reinforcement learning framework. Okay, and then because we have a linguist on the team, I mean, not as great and as many linguists as here, we have only one. We did some manual analysis. So for one of these tasks, all of the changes made with XARELLO were just manually analyzed by someone trying to find some patterns. And the changes that the model makes are the following. So first, it likes very much to change some word tokens, right? So if you have vocations, this is split in many subwords in transformer, right? So it changes vocations into vasations and changes hypocritically into hypoclipically. And what it achieves in that way, it achieves a word that looks very similar, is very similar according to edit distance, but it's a completely unknown word for the victim classifier, right? So it does learn, it doesn't change individual characters because it doesn't understand the visual similarity, right? It's just word IDs. But it does understand that if you change like a small part of a longer word, you will get a good score. The second thing it does is because in low credibility content, the one feature that is always present is the emotional charge, right? So if you have emotionally charged words, it's quite a strong indicator. So what it tries to do is it tries to tone down words to have words that are less strong, right? So instead of like his aggressive behavior, it will say his own behavior, which probably fits the context quite well, but removes this strong wording edge here. Changes injustice to word. I don't know if it fits the context. I would have to see, but it's definitely like removing the strong sentiment in these words. And then sometimes, unfortunately, it doesn't obey the grammar as you would like it to. So spreading words, it realizes that worse is a strong word. It wants it to replace with bad. I'm not sure it's a less strong word, but obviously it does it in a way that you create a word that doesn't exist again, right? And yeah, it also likes to remove words. I said that we don't have like word removal, but maybe you can remove a word by replacing it with a comma, for example. So if you remove this gaping, which is a very strong word, like it's not good enough, right? You get like a malformed sentence. Yeah.
Well, sorry, what would be the advantage of doing this with an established large language model? What disadvantage?
Well, this is already uses a large language model.
Yeah, but say ChatGPT wouldn't make these kind of mistakes, I suspect. Like there's some.
So yes, yes. So we have a paper that is incoming with using a large language model to replace, instead of doing word replacements, using a large language model, ask it to rephrase. And what happens is you get better quality text, but it might not be as good for attacks because you will never get this, as you said, right? So you have these two goals that you want to fool the model, but you want to generate good text. And if you replace word replacements with a large language model, you get better meaning preservation, but unfortunately it doesn't do these things, or at least we didn't know how to prompt it to do that. It likes to generate, and like it has also a very big disadvantage. It's very jumpy with anything that looks remotely controversial. And we're dealing with fake news here, so there's a lot of controversial stuff. Forget about paraphrasing a sentence that has any reference to Jews. No Jews, no racists, nothing like that can ever get mentioned. Even though I'm not asking it what should I think about the Jewish religion. I'm asking, can you paraphrase this sentence? But no, it will remove anything that is remotely controversial. So, and then in word replacements, it doesn't care. Okay. So just a bunch of limitations to mention. So yeah, so the first thing, it doesn't quite work with these news articles, and this is because of the search space. So probably this adaptation phase, when we do like 5 steps and then we cut, should probably be changed. At least give the model longer time to make a change before you move on to the next steps, because it just doesn't have the opportunity to explore it. The action model is probably too simple, right? So we just do single word replacements. And yeah, so you can do deletions. Deletions are quite strong. Sometimes you can delete a word and the sentence still holds. And yeah, this is the work I was mentioning. You can do like multi-word replacements, and you can get like quite high semantic similarity with large language models. But there's a price for that, right? More actions means you need more training, which takes time. And the same with other limitations. So reinforcement learning is famously very hard to set up and make it converge. And there's many parameters which are kind of chosen based on trial and error. And you could do systematic search, but it just takes computational cost, right? Because we make all these changes, and then every change we make is a prediction from we use Roberta, I think, And then the victim is also asked, and it's also a large language model. So it takes like 10 hours to do just one victim, one text round. And then we need many experiments. So yeah, we have to pay for that. And then, yeah, even though this everything I've shown is essentially applicable to any kind of text classification, but I only show like these 4 tasks. You can try it on other misinformation detection tasks. You can try other content filtering tasks like head speech or all other stuff. And also, unfortunately, everything is on English because the misinformation data are also notoriously hard to obtain because it's a complicated issue socially to say, you know, a certain medium is not reliable. So it's hard to get very good data sets. But obviously it's possible to expand this to other languages as well. Okay, so I think all that's left for me is to thank people. So first of all, from the people from the team at UPF who helped in preparing this, and the founders. So this was during the Marie Skłodowska-Curie postdoctoral fellowship, and also the Grid contribution was very welcome because, as I was saying, it's a lot of computations. Yeah, these are the links to the project, which is actually finished, but it's all about finding adversarial examples for misinformation. And then XARELLO is published already on a workshop for social media and sentiment and emotional analysis. Okay, thank you very much.